In this video, we're going to talk about cumulative density functions. A cumulative density function, which we'll be abbreviating in the future as CDF, is just the probability of getting a value less than or equal to some threshold value. We're going to first talk about how we measure this in the case of a discrete random variable. And in that case, there are n possible outcomes, x1 through xn, and the cumulative density function just describes the probability of being less than or equal to each of those potential values. Let's consider the case of a single roll of a fair die. There are 6 possible outcomes, 1 through 6, and the probability of a 1 or less will happen only if you roll a 1, which occurs 1 out of 6 times. You get 2 or less if you roll a 1 or a 2. The probability of getting less than or equal to 2 will occur 2 out of 6 times, or 1/3 of the time. 3 or less would occur 3 out of 6 times if you roll a 1, 2, or 3. So the probability of that is 3/6, or 1/2. The probability of getting a 4 or less is the probability of getting a 1, 2, 3, or 4, which would happen 4 out of 6 rolls of the die. And that would happen 4/6 of the time, or, for simplifying, 2/3 of the time. The probability of 5 or less would happen 5 out of 6 times. And the probability of 6 or less would occur 6 out of 6 times, because you always end up in a single roll of a fair die with either a 1, 2, 3, 4, 5, or 6. So that's the cumulative density function. So this table here represents the cumulative density function for the random variable, which measures the outcome of a single roll of a fair die. The same concept applies when we talk about a continuous random variable. We're measuring the probability of being less than or equal to that threshold value represented by a lowercase x here. If we assume that student weight is normally distributed and it follows this bell-shaped curve here, the probability of being less than or equal to a value of x is just the area under the curve to the left of that point. That's something that you worked on in your introductory statistics class using either a standard normal table or a standard normal calculator, which lets you calculate the probability that a normal variate will be less than or equal to any threshold. This image here represents the probability density function for a random variable which measures the distribution of student weight in a given population, let's say at some college. This appears to be roughly a normal distribution, that sort of bell curve that you've worked with quite a bit in earlier courses. The probability of being less than or equal to any threshold value is just the area under the PDF up to that threshold value. We can also directly graph the cumulative density function, which tells you what the cumulative density is at any point. In this case, student weight has a lower bound of 0, and we tend not to observe any college students just floating through the air. So we generally don't start observing any significant density until we get up to somewhat higher weights. But the probability of observing a very low weight is very, very low. But as we get to the thicker part of the PDF, the cumulative density starts rising faster and faster. And then as we start moving out into the right tail of the distribution, the CDF will asymptotically approach 1. So as student weight tends towards infinity, the cumulative density function will approach 1. As we move off towards negative infinity, or 0, in this case, the cumulative density function will approach 0. So what we know is that the CDF will always be between 0 and 1, and it rises very rapidly in the parts of the distribution that's somewhat thicker. If we want to measure the probability that a random variable is above some threshold value, then we just take 1 minus the probability of it being less than that, because we know the entire area under the curve adds up to 1. So the area below the threshold plus the area above must equal 1. So to get that upper tail, we just take 1 minus the area in the left side of that distribution. Similarly, if we want to find the probability that a random variable falls between A and B, where of course B is greater than A, we can measure that by just taking the cumulative density function evaluated at point B and subtracting the cumulative density function evaluated at point A. Looking at this diagram, imagine all the area shaded to the left of point B, and that's a CDF at B. Then we subtract from that the amount to the left of point A, and what we're left with is that gray shaded area in this diagram, which is the probability of being strictly between A and B. Let's take an application. Suppose we have a continuous variable, which is a distribution of income in some population, where 5% of the population earns less than $10,000, 35% earns less than $30,000, and so on down the table. So suppose we wanted to compute the probability that income falls between $30,000 and $70,000. We know that 85% of the population receives less than $70,000, 35% earns less than $30,000, which means the amount between those two values would be just 85 minus 35, or 50% of the population must fall between those two outcomes. Similarly, if we want to find the probability of someone earning more than $90,000, we know that 92% of the population earn less than that, which means we just have 8% of the population earning more than that. You've done lots of work with this in your past courses, and we'll be using these concepts quite a bit in this course. So it's important that you recall how to use these basic measures.